Hello, my name is Ed Friesema. I'm a student at UNLV in the PhD program under Dr. Fontes, and this is my presentation for CS715. I'm going to slideshow. Okay, my presentation is on using Qiskit to analyze and simulate Bernstein Vaxraini ALgorithm. Qiskit is a Python framework, more like a library of tools that IBM has used to become the interface language for their quantum computers that they're putting online and developing. So it's kind of a whole tool suite. There's a lot of reason why I chose Qiskit over some of the other options was that it's online. It gives you you can actually work with real quantum computers using this, and it's very intuitive user interfaces, I hope to show. Okay. So, why quantum computing? Well, like we talked about earlier in the class, or Professor Bine showed us, P versus the NP complete problem is a huge issue. Like, there are a lot of problems that if we could solve NP complete problems in polynomial time, we would be able to do a lot of things that we just can't do today. So quantum computing, for the first time in a long time, since computers really started, and von Neumann basically lined up the architecture that they're all built on, and Turing showed computationally what their theoretical limits are, we've been dealing with the same type of computers. They've been getting faster, incredibly faster, and getting more memory, but they're still fundamentally limited. So what are the pros of doing with quantum computing? First is it offers the possibility of true random number generating. There is a whole mid-level of theories where there's an idea that you can use something called a probabilistic Turing machine, which is just a Turing machine with the ability to, instead of deterministically going to the next state, using a probability function. Now, that's not necessarily exactly the same as a quantum computer, although it shares a lot of properties, but it is, even that they've proven has the chance of solving problems that we couldn't solve normally. So even just the true random number generation instead of the pseudo-random number generation that we currently use for Monte Carlos and for Las Vegas algorithms, other probabilistic algorithms, even that is an improvement that could offer us a chance to do some things better than we currently do. Then it offers something, and this is why Richard Feynman, who was a physicist who first thought this up, he was talking about how it was very complicated for computers to simulate quantum processes, and it would be easier if we just had a computer that used quantum processes. Then the simulator would actually just be the computer. If you could set it up, whether it's the spin up or spin down of an atom or the polarization of a photon, it doesn't, as far as the quantum mechanics equations are concerned, they're the same. So as long as you can represent one two-state problem with another, it would be probably much faster just to run a quantum simulation of it. So that's one area that quantum computing could definitely provide an advantage over the classical computers we currently use. The third biggest thing, and the real holy grail, is the idea that we could actually tackle NP complete problems that the current computer architectures cannot. Shor's algorithm is one of them. It was something that a guy came up with, Peter Shor came up with in 1994, that could factor large numbers using a quantum algorithm. It was the first quantum algorithm that really showed a speed up over classical machines. Obviously, factoring large numbers means RSA becomes very leaky, very attackable, and so that was something that we decided that was the first thing that woke people up to quantum computing being something we really should look into. Okay, some of the cons. That current state of technology, these gates elements are really error prone. The way they tend to deal with it is they make a lot of the systems they're making have thousands of qubits, and actually but they claim to only have 20. In other words, they're using a lot of redundancy to make up for the fact that these things are very unreliable. Another big problem is that the entanglement state is hard to maintain, and it gets harder the larger the number. So the closer we get to actually doing problems we really want to do that are really interesting, the entanglement state's getting harder. Some pessimists say that we'll never be able to entangle enough qubits to make these things a useful proposition. Predicting the future and saying never has proven to be a really good way to get in the history books as an idiot. So I'm not going to sound off on that argument. A lot of smarter people than I have said, well, this will never happen. But people always find out new ways to do things. And another big problem for me, and this is one thing that just struck me as a coder myself, is the fact that there's no known way to check. Once you measure at any point, a quantum circuit at any point, you collapse the superposition. And as I'm going to show in the next slides, superposition is everything. So while you're developing an algorithm, you might be able to check the intermediate states. Once you actually try to get the full thing running, you can't check anything intermediate while you're doing it. And obviously the programmer in me looks at that and says that's a huge possibility for making this very, very difficult to develop things as they get more and more complex. Okay, so I'm going to go into now I'm not going to make this a lecture on quantum mechanics. I don't understand quantum mechanics very well. I can't do anything but the simplest problems in it. I've tried to spend a lot of time reading about it to understand the theory and the physics behind it, but I gotta admit I don't. Or at least there's a lot of stuff I don't understand. So I'm going to just go into the basics of what I feel is essential for what we're doing, which is actually making quantum algorithms. So the basic difference on the simplest level is that instead of a normal binary bit of 1 and 0, you have something called a qubit, which is a quantum superposition of two states, which could be called 1 and 0. The superposition goes back to, if you've heard of the Schrödinger's cat paradox, the idea that something can be in two things in some spooky combination of those things at the same time. That's basically the heart of quantum mechanics. All the things about the two-slit experiment, anything you might have heard where quantum mechanics sounds like it's weird and it doesn't act like classical mechanics, it's because of the property, its ability to do superposition. But one difference that you might not know, or that is very different when you talk about superposition in quantum mechanics versus superposition in, say, linear algebra, is that in a lot of other linear systems, superposition means you can put a lot of different elements together and they will add up linearly. Like if it has a small contribution of one element, when you add it into a bigger system, it'll still have a small contribution to the output. As far as we can tell in the physics, superposition in quantum mechanics is pretty much limited to two things. It is very hard to entangle, and I don't even know if it's possible, to entangle 3 different states or more. But you can do a lot of combinations of 2 different states with things. And that's where quantum teleportation comes in. Quantum teleportation is not like Star Trek. It does not mean moving something across the world in the same space. Quantum teleportation basically means you've taken a superposition state and without collapsing it, because remember, every time we measure something in quantum mechanics, we collapse the superposition. Quantum teleportation is the idea that when you take you can add a quantum state and transfer it to another one without having to make the measurement. So that allows us to this is where we can start building complicated systems, because if we teleport one qubit into another, and then another qubit into that, and another qubit into that, then we can start making quantum circuits that can deal with 8 bits, 16 qubits, even more. But the catch is that maintaining that coherent state where the superposition has not been collapsed, maintaining that what physicists are calling entanglement, gets harder. The more pieces you get in and the longer you try to do it, it gets harder and harder. And that's the key challenge right now for a lot of people developing the hardware for these systems, is how do we maintain this quantum entanglement, this superposition of states for a long time, for as long as possible without collapsing it. Right now it's like in the order of milliseconds, and they're trying to obviously get it longer. There have been some reports of satellite things where it's lasted for a very long time. There's a lot of people doing research on this on a lot of levels. But the basic fundamentals is the quantum weirdness is about superposition. The longer we can maintain that superposition, the more complicated algorithms we can attempt, and the more interesting things we can try to do. The moment that breaks down, whether it's called collapsing the wavefront or decoherence or once we lose that entanglement, then basically we're back to being in a classical machine. Okay, so now how do we manipulate these things? These are where we come up with gates. There are lots of gates available. There's not just the controlled NOT gate. There's not just the Hadamard gate. You will hear lots of names about these different gates if you look into this. They all do different things, but basically, like the controlled NOT gate here that is shown here, that's one of the fundamental ones. It basically acts like an XOR gate in the fact that the bit on the top, the one-state bit, controls the bit on the bottom. So if the bit on the top is a 1, it will flip the bottom bit. If the bit on the top is a 0, it won't do anything to the bottom bit. So the results is for those two bits is that you basically get an XOR function. Now the nice thing about this is this can also maintain superpositions of states. The superposition states can go through the XOR gate and be manipulated without losing their superposition, and that's the key. So we want to maintain that superposition throughout the entire algorithm. Once that collapses, we're done. So, but that's what an entangled state is. So when we're talking about all these things, superposition, decoherence, entanglement, is basically the same thing. We're trying to keep that quantum state unmeasured until we actually are done. Now, there's lots of ways to read it if you read it. If you read more classical physics books, you get what's called the Bra and Ket vector notation. That was come up with a physicist named Dirac, and it was basically Bra stood for, since it was a bracket, he made it Bra and Ket, and really clever. So bras are basically row vectors, and kets are column vectors. And a lot of the operations, a lot of this really boils down to linear algebra. Or that's how the basic mathematicians, notation and mathematics are done. So the second notation, matrix notation, is actually the most common. All these gates that I'm going to show you, all these operations, can be reduced to a linear algebra form. Now it's a little trickier than regular linear algebra in the fact that these can be complex valued pairs. But it still, for me, the matrix notation, since I've done linear algebra, is the easiest one to understand and just kind of see, okay, this is how this works. Like what I'm showing you here, the first matrix, the zeros on the diagonal and the ones on the other points, that's basically the matrix notation of a Hadamard matrix, which does an entanglement of it, and it's a very fundamental gate. So it basically, if you just looked at it as spatial rotation, it's just a space rotation, but it actually allows you to create a superposition of states in the physical quantum circuit. And the last way is called a Bloch sphere. Basically, the 0 state is a vector pointing up, the 1 state is a vector pointing down. If I pass it through the X gate, that's basically saying, okay, rotate that 180 degrees around the x-axis. A Y gate, 180 degrees around the y-axis. A Z gate, you get the picture, 180 degrees around the z-axis. So Bloch spheres are kind of another more visual way to represent what's going on. They're obviously not that useful when you start getting into big circuits, but when you're just playing with this and learning with this, sometimes I find this is a very good way to think about how these gates are operating. Okay, so some of the challenges that are ahead. Like I said, maintaining coherence. That's the big. Almost all these, in a lot of ways, boils down to how long can we keep this coherence, the superposition state, alive. The next thing is, and forgive me if I throw in anthropomorphisms, the next thing is monitoring performance. Like I said, if you measure these circuits at any point in the operation, it will collapse the waveform vector. So you do not want to do that. But that makes it very hard to debug. That makes it very hard to track and make sure that something isn't, if something went right before and then you change something, that you don't have to go back and restart the whole thing. From a developer's point of view, this is actually one of the biggest problems I see, and something that I hope we can find some way to improve. So error correction and quantum information. This is where there's a lot of work that can be done. If you know anything about error correcting codes in the classical sense, there is a lot of need for this in the quantum sense, and hopefully I'll be able to show you why that's the case and demonstrate it rather than just telling you. But it's very important that we understand new error correction codes are going to be needed if this is going to be used on any significant level. And a lot of these error correction codes and the need for that has been recognized. So information theory. If you've used information theory for Hamming codes or Viterbi codes to analyze those, we now realize that there's a lot of importance to making a quantum information theory. And there's a lot of development working in that area. And the irony is that, like I said, these things are not really reliable right now. These components give a lot of different results. And that's a big problem, obviously. We want reliable computers. The funny thing is that if you go study the history of computing, back in the day before integrated circuits, when these computers were all vacuum tubes and John von Neumann was at Princeton with UNIVAC, it was very common for these parts to be considered unreliable. We're used to, in our IC microprocessor days, to have very reliable billion, trillion bit transistors circuits on our chips. But in the beginning, these were they were tubes. Like when they talked about bugs in the software, they meant literal moths and spiders getting into the circuit and screwing things up. If you read Turing's Cathedral, he talks a lot about the Princeton days and how they had to be able to come up with algorithms where they could get reliable results even when the individual circuits were unreliable. So they had to redo this, and they had to build this from scratch. And so it's funny how things sometimes come full circle. And now, after being so long of assuming that, my laptop's going to be, that bit errors in my laptop aren't even an issue that I have to think about, now we're building a whole new class of computers, and unreliable parts, at least for a while, looks like it's going to be a serious problem. Fortunately, like I said, some people have already dealt with this, but this is a challenge we're going to have to face again. So I'm going to show you a simple algorithm here. It's called the Bernstein Vaxraini algorithm. It's a simple thing, but I think it shows off how quantum computers can really maybe change how we do things. So it starts out, if you needed to guess an n-bit number, there was an n-bit number, say we're going to go with 6 bits, in a black box, and you could only ask yes or no questions, how many questions would you need? We've done a lot of kind of search algorithms like this and sorts. And for classical computers you need n. You can do it in different ways. You can make it an AND gate. You can do a comparison where you're saying, okay, for 64 bits, is it greater or less than 32? Okay, it's greater than 32. Well, then you got the first bit as a 1. The next one, is it greater or less than 48? Okay, then the next bit, if it's less than, then the next bit is a 0, and so on. But you need to ask n questions. For a quantum computer, how many do you think it'll take? The answer is, for a quantum computer, it can do it in 1. And as long as it can maintain the coherence between as many bit qubits as that number is. In other words, if you can have a 16-bit qubit quantum computer, it can do it up to 16. It could do it up to 32. It could do it up to 64. As long as, if you have as many qubits as that computer, if you can maintain coherence between that many qubits, you can answer this question in 1 step. Which I hope is like you realize that's a big deal, and that could make a big difference in how these things work. So now I'm going to go to VS Code and show you a little bit about how these things work. Okay, so this is, again, I wrote it in Qiskit. This is Python. If you don't know Python, the language hopefully is pretty simple, but you can kind of get an idea of this. So the first step is just to import the tools that we need from Qiskit, which you can install. The next thing I did, just to make it easy to see what we're doing and to change it when I needed to, is I basically made a string of a secret number. This is the number we're going to try to guess. So it's 1, 0, 1, 1, 0, 1. Now, the next step, so I ran that. The next step is, this is basically setting up the basic circuit. It's basically setting up, so we need n qubits and then an extra qubit just to do the superposition. So we're making a quantum circuit n plus 1 long, and we're putting the .h, this .x means basically putting a NOT gate on the circuits that I need. Meaning turn it 1 when it assumes that all the inputs are 0. So if you just NOT the input, that means you're setting it to 1. More complicated circuits obviously can be different. And then the .h means setting up that Hadamard matrix. It means setting up, that's creating the superposition state. at first, these do not start in a superposition of states. They start just like a classical computer, either on or off, 0 or 1. We need the Hadamard matrices to start getting the quantum phenomena. So I can draw this out, and this is a nice thing. It uses matplot library, so it just draws out a nice graph. This is really, all I had to do was say circuit.draw, and it drew out what I built here. Okay, so you can see we got 6 bits plus the 1 control. Think of it as a control bit for the circuit. And these C1s are the classical. These are what we're actually going to measure in output, because you can't measure these without collapsing the superposition. And then this barrier is just kind of a shutoff. It says, like, okay, this is where we've created these states at this point. So the next thing, this little circuit right here is just basically going through my secret number and setting, it's hard coding the number that we want to guess into the circuit. So, and then adding another set of Hadamard matrices to the output. So in this case, it's Q5 is the most significant bit. So it's just 1, 0, 1, 1, 0, 1. That's basically it. Every one of these X gates allows it, is basically treated like a NOT gate to the circuit that's out there. It's basically saying this is set to 1, so it's flipping all these bits. And then we have another barrier and our Hadamard matrices on the outside. So the next thing we need to do is measure. We are measuring our system. Boom. We measured all the bits. That's what just means the measure. So we've collapsed it. We've measured this all out into the classical bits. Now we are actually going to run the simulator. The simulator is a quantum. It's a classical Python program that simulates the quantum algorithm. There are lots of simulators depending on what you want to look at, but QASM is kind of the easiest one to use. So basically, we run it, and I'm only going to run one shot because I said I wanted to guess this in 1. So you can run it multiple times because a lot of these things are statistical. You want to see lots of different results. But basically, I'm just executing the circuit and then seeing the results, seeing how many counts I get. And with 1, it got it right. 1, 0, 1, 1, 0 in one shot. Now, I know some of you are probably at this point saying, Ed, you cheated. I can look at this circuit and I can totally see that you have I see the wires. It's like the Wizard of Oz. The wires are right there. I can see it's hooked up. You didn't do anything special. You just read that base. Well, and part of this is you're going to have to trust me on this, but this barrier means that no, it's actually doing a Hadamard matrix. What's really doing behind the do is instead of doing all those, imagine it like a cashier. Let's say I had a ticket for a race where instead of just one winner, it was possible that 2 or 3, any horse that finished faster than a certain time won. So let's say I had tickets for all 6 horses in that race, and I wanted to figure out who won and all the horses that won. Well, in a normal casino, let's say there was only one, like a classical computer, there's only one gate. I'd have to send each person the ticket and check, did this horse win? Did this horse win? Did this horse win? And then find out the ends of results when all 6 of them had gone up. But in this case, what's really happening is I get to send all 6 people with their tickets to 6 different cashier windows at once and get the answer. So that's the power of superposition, is that it allows us to answer these questions in a massively parallel fashion. And that's the power of doing it. Like I said, I could change this. Let's say I could make it something bigger. Let's say I said, like, okay, let's make it 8 bits. So let's make it another 8 bits. Then I could do this. Now you can see I got... So now I have more bits here. I can run that. So now I have more bits on this one. And then I can run the simulator. And now it guessed the new number. The new 7-bit number that I put out there. So this is the basics of Qiskit. Now the last part about it, and the really cool part in my mind, is that it allows us to throw in a few extra things. You can actually test this on a real quantum computer. And before, if you've gotten really excited up till now and said, look at how amazing this is, he did this in one step, I'm going to show you that... Okay. So you can actually use this to, once you built a circuit, you can send it to a real quantum computer. IBM's got a list, and which you set up an account on their IBM Q experience, you can actually use and submit jobs to a real quantum computer. Now it shows it's queued, it shows about 1. I'm going to go on and then come, okay, job is actively running. Okay, maybe I'll wait because this is coming on. So now it's actively running. This is actually, now I'm running the circuit on a real quantum computer. Job is successfully run. So now I can run it and get my results, and it'll be amazing. And whoa, look at that. It's kind of ugly, isn't it? Yeah, because this is what a real quantum computer does. And this is what when I went back to talking about unreliable parts and error correction needed, this is what I mean. This is the state of the art right now. So there's still work to be done. So hope I didn't get anybody too excited, because there's still, this is the reality. But the cool part, or the takeaway I want, is that look how quickly you can go from having a circuit idea or an algorithm to actually running it on a real working quantum computer. Just remember that the software simulator gives you an idealized version of it. So we still got a lot of work to get it so that our real computers can do what we need to do. So I'm going to go back to the system, go back to my slide presentation, and talk about, so like I said, there's a lot of areas where this can go on. You can simulate quantum systems like Feynman said. We can use probabilistic Turing machines to do Monte Carlo and Vegas algorithms. There's a lot of talk about that. If you haven't played with Monte Carlo and Vegas algorithms, even on a classical machine, it's actually pretty amazing what they can do, and they're definitely worth checking out and working with a little bit, especially when you tie things like Monte Carlos to Markov chains and other types of state machines. It can really, you can do some amazing things. And quantum computing is probably an area where that's going to be developed even further. Error correcting quantum codes. If you like codes, if you like puzzles, if you like cryptography, there's a lot of work that needs to be done here. And for me, just because I was an electrical engineer as an undergrad, I love Fourier series. They do an amazing tool, and when I found out there was a Fourier quantum algorithm, I wanted to figure it out, because Fourier series are incredibly powerful in classical signal processing. If there's a quantum algorithm version of it, I want to see what it does. So that's my thoughts of it. Resources if you want to go further. YouTube channel, all of what I did with there is in the YouTube channel for IBM Qiskit. And so it's just a simple Qiskit channel on YouTube. If you're more interested in maybe Microsoft's version, Microsoft has a language called Q#, which is relative to C#. If you're used to doing ASP.NET or web forms, Q# will probably look pretty familiar to you. I would say the only real difference is I liked Qiskit's documentation a little better. I thought it was more comprehensive. But if you definitely want to work for Microsoft on the quantum computing research, then definitely learn their system. As far as books, this is a new field. There are not a lot of books that are out there. I said the best one I found is this Nielsen and Chang Quantum Computing and Quantum Information. It's the only one that has a significant portion of the book dedicated to quantum information theory, so which I think is going to be very important as this discipline develops. The other thing that I think is important is there's Quantum Mechanics for Engineers. This is actually a website. There's no physical book, but it was to me the most intuitive because it stuck with the linear algebra. It didn't try to do Schrodinger's wave equation, so it was one of the easier ones. The other one is Richard Feynman. He has his series of lectures, his lectures on physics. The third volume is all quantum mechanics, and it's tough going. It's tough sledding to get through it, but there's a lot of stuff in there that's worth understanding. And then information theory. I think information theory is going to be a huge part in this. So Shannon Weaver's Mathematical Theory of Communication. Pierce, who was Shannon's advisor at Bell Labs, wrote an Introduction to Communication Theory. Those are great places. If you want to see some of these algorithms and see other ones that are available, go to the quantumalgorithmzoo.com. There's a load of them. They also have analysis on like how much faster they think these new algorithms can be than the quantum ones. There's tons to look at and to look through. Thank you very. If you want to see any of this, I'm putting it up on my GitHub site, so you can look at it. My name again is Ed Friesema. Please feel free to look me up. And if you have any more questions about this, thank you very much for your time.